Okay, so with this, we will essentially finish the story about crystalline and quasi-crystalline materials. And before we move forward, are there any questions? Okay, if not, let me just remind you, where do we stand in terms of the roadmap in the structure part of this class. So we basically covered non-crystalline material. We talked about crystalline material and symmetry. And the next thing that we will learn about is yet another class of materials that are called liquid crystalline materials. And when we finish this discussion, we will have one more lecture about that. We will start the discussion about defects in materials, okay? So today we will start the discussion about these liquid crystalline materials, and this is just an optical image of such a material, okay? So the liquid crystalline materials, the name itself seems contradictory because it tells you that it's liquid and yet it's crystalline. So we have to learn what that actually means. The other thing about these materials is, except that they form these beautiful images when you look at them using optical microscopy, they're also technologically very important. We will see that there are many materials that you don't even think about liquid crystalline materials that are actually liquid crystalline form of matter. So, for example, soaps and many lubricants, they happen to be liquid crystalline materials. So defining what these materials are and knowing how we define their structure and describe their structure is extremely important, okay? So let's first remember, again, when we talk about liquid crystalline materials, let's remind ourselves, what did we learn about liquids and crystalline materials? So what was the difference between liquids or amorphous materials and crystalline materials? So that's a question. Yes?
Crystals have long-range order and liquids?
Yes. So the liquids have, and amorphous materials have only short range order. So amorphous materials do have short range order, but they do lack the long range order. And crystalline materials possess both. So I can also ask you a question, because this is the concept that we will use as we go forward. What are the structural descriptors that we use to describe these materials? So if I tell you, tell me at least one descriptor that was used to describe amorphous materials, what would be your first answer? Pair distribution function, that's right. How about crystalline materials? How did we define, in general, crystalline materials? What were the appropriate descriptors to be used? For example, lattice, basis vectors, unit cells, etc., right? So it is just defining what is the translational order of the crystal itself, right? So we will see that, again, pair distribution function is the function that can be used to describe liquid crystalline materials as well, but there are more appropriate ways to use them or to describe them, okay? So in order to understand what the liquid crystalline materials are, we have to first understand what actually means long and short range order. Or in other words, what does it mean that we have positional and orientational order? So we will see that the liquid crystalline materials are usually highly anisotropic, meaning that the molecules that constitute liquid crystalline materials are either relatively long or have the disc-like shapes. And they have this anisotropy, and for that reason, they can have positional or orientational order. So when we talk about the long-range positional order, what that simply means is that you can define a lattice, right? If you have a crystalline material, the long-range translational order simply means that you can define basis vectors T1 and T2 in two-dimensional space that will completely describe this particular material in a long range. And that's simply the positional order. So now you can think about molecules that are highly anisotropic, let's say that have a rod-like shape. So if I think about the long-range orientational order, what I mean by that is that all of the molecules in a long range have the same orientation. And I really don't care about their position at the moment because I'm simply talking about the orientational order. So if you merge these two concepts together, if you have these highly anisotropic molecules that are ranged in a long-range positional order, you will end up in a crystal that is composed of these molecules, but they will be arranged in space in a very ordered fashion. This is not very ordered, but it should be. Okay. So this would be the definition of my crystal. So we will see that liquid crystalline materials are the materials that have the long-range orientational order, but they lack the translational or the positional order. Right? So the liquid crystalline materials, the name itself tells you, is that they do have properties that belong both to crystals and liquids. So what is common between liquid crystalline materials and crystals is that they both have the orientational order. Right? But in the case of the liquid crystalline materials, they will lack this positional order, which is typical for liquids. So before we actually talk about liquid crystalline materials, I would just like to mention yet another class of materials that is called plastic crystals. And what they have in common with the crystalline materials is that they have the positional order, meaning that the molecules that constitute this particular material are arranged periodically in space. So we can define a lattice in this particular case. So I can design a set of points that will be defined by two vectors T1 and T2. But the orientational order won't be preserved long range. What that means is that if I have a molecule that has a certain shape, and if that particular molecule has a certain orientation at one lattice point, and the neighboring lattice point, it can have a completely different orientation. So when you construct this particular material, it will have this type of an arrangement. Again, the position of the molecules or the motifs will be precisely defined by the basis vectors, but their orientation won't be. And so typically these materials have this spherical type of shape. So what that means is that they typically can very easily rotate around their axis. So they are somehow confined in space by the presence of other molecules in this particular plastic material, but they can rotate around their lattice point. So what that means is that if I take this molecule and position it here, the neighboring molecule can have completely different orientation. So these were just two examples of them. They happen to have this particular stoichiometry, C2Cl6, C8, H8, etc. So this is called cubane, etc. So there are different materials that do form these plastic materials. And the name plastic crystal comes from the fact that they're typically relatively soft. And the reason for that is that the forces between these individual molecules in the material itself are usually van der Waals forces. So again, these materials do exist. They don't necessarily have too much of the application, but they do have in common with crystalline materials the fact that they have this long-range order.